morning, everybody. First of all, well, I am glad to be given the opportunity to talk. So, I'd like to talk about the study of pitch rotations in soft matter systems using optical tweezers. This is the sort of outline of the talk. I'll give you some basics of optical tweezers and then talk about the thing and all this. So, he was once in 1969, he was sort of fiddling around with, he wanted to trap actually a particle between two traps, like two beams like this. So one beam focused in like this, the other beam focused in like this, and he was trying to see if you could sort of hold a particle here in the middle. Instead, he saw something very interesting. He found that these particles were coming in two directions from both sides, and the third direction, the axial direction, it was getting kicked out. It was getting kicked out. So that he reported here in one of the first papers in physical PRL, and then he used two beams to sort of trap it here and control the axial position. And after that, what he did was in 1989, I believe, this is 85. So here he sort of showed that you can use a tightly focused laser beam, a very tightly focused laser beam, to sort of trap the particle in the focal plane actually. And this is the famous gradient force here, the gradient force here that sort of confines the particle here. And there are two competing forces. One is the scattering force and the other is gradient force. The scattering force pushes slightly away from the focus. The gradient force traps it in the focal plane actually. So based on that, I'll start about rotations. So a rigid body, as I was telling you, can have 6 degrees of freedom, 3 translational degrees of freedom and 3 rotational degrees of freedom. The translational degrees of freedom are well understood in optical tweezers literature. You can study them very well using quadrant photodiodes, where you have 4 quadrants, split photodiodes. The right half minus left half gives you X, and the top half minus bottom half gives you Y. The total intensity over all 4 quadrants gives you the Z axis because it's a kind of an interference between the scattered light and the unscattered light. However, if you come to rotations, you can also have three ways in which it can rotate, the particle can rotate. So only the in-plane rotation was so far studied in the literature. It was done by Professor Helena Rubinstein Dunlop from Australia, that if you have a birefringent particle and you have a polarized beam of light, you can actually turn the axis of polarization and the particle will follow, and you can actually generate controlled rotations, controlled torques. So, but then that still left out the 2 degrees of freedom that are the out of plane degrees of freedom, the pitch and the roll. I call this one the yaw axis. In the nomenclature of the airlines, this I call the roll axis, this I call the pitch axis, this I call the yaw axis. So in the nomenclature of that, we have been calling this the pitch rotation. So how do I get to that? This is only beginning to be studied in the past 1 or 2 years actually. We have done a lot of work on this thing, and there is some work on by Professor Helena Rubinstein herself and some other groups. So the pitch degree of freedom I am focusing on in this particular talk. So for that I am going to be requiring these birefringent particles. These are same thing as what Professor Rahul Mangal talked about. These are liquid crystalline particles. These are RM257 if you want the technical nomenclature. So it forms a colloid. If you do it properly, it forms a colloid, but it's birefringent also. So it has a refractive index which is in one direction it will have a high refractive index, in the other 2 directions it will have a low refractive index. It is kind of a bipolar structure if you look at the directors. So you can then trap it in a linear polarized light and then put it on the cross polarizers. As you turn the axis of polarization, this goes from a bright spot to a dark spot, just like you'll expect for cos square theta dependence. So now please note that the dark spot is not perfectly dark. Now that is the underlying hypothesis for the entire thing that I'm talking about today. This dark spot is not completely dark. It has got 4 lobes in it. The assumption is that as it turns in the out of plane sense, there would be an anisotropy built up in the scatter pattern, and you can study the scatter pattern and find out how much it turned by. So that's the kind of the underlying assumption. So for that we did a simulation. This is one of my first works here. I borrowed some data from Eric Schaffer's lab where I was a postdoc, but that's why I sort of put his name there, but the simulation is entirely mine. So this, if you put it on the cross polarizers, you're going to see, I model this thing as a kind of a sphere with a kind of an ellipsoid with two different refractive indices, and then it becomes a sort of a birefringent particle, and then it has got a four-lobe structure. Two of the lobes, this four-lobe structure has got four scatter. This is a scatter pattern and under cross polarizers. So, and then as you turn it in the pitch sense, two of the lobes will glow brighter, two of the lobes will glow dimmer. So then you can find the anisotropy in the halves to find it out, to find out how much it turned by. So this is the kind of trend you get. You can find it out from there. It works particularly well if you're aligned like this, and then you get a straight line curve here. It goes from 60 degrees to actually about 70 degrees to minus 70 degrees. It shows a very nice linearity. And as the difference between halves gives you information about the angle that it sort of is in the pitch rotational angle. So this was published in Journal of Optics earlier. And then I extended this thing to a high resolution. That the previous thing I borrowed, I did it with microscopy. Then I went to optical tweezers, and I sort of started with a linearly polarized light, put it under cross polarizers, and then took the scatter pattern, put it into a split photodiode. Basically, that will also have the difference in halves information. And from there, you can find out at a very high resolution that you're going to have this pitch rotation. So this is again the theoretical curve. Here is sort of so about 60 to 70 to minus 70. It sort of works pretty well. So there's kind of a linear trend here. And recently, Professor Ayan Banerjee from IIT Kolkata, he has also done some experiments. This is with this structured beams. So he has used that, and he has sort of managed to spin this thing completely in the pitch sense using one single beam. I'll tell you how difficult that is. It is notoriously difficult. And but he is seeing the scatter pattern. You see the scatter pattern. It's going from two lobes to one lobe, two lobe, one lobe. It's spinning constantly, and it's kind of the lobes are splitting and coming together, splitting and coming together. So this is basically what is happening here in my thing. If you change the axis of this cross polarizers, you will get four lobes also. You'll see the four lobes also. So this is the pitch rotation that I'm talking about, and he sort of confirmed my sort of the entire hypothesis. And then I sort of went ahead, and now I'll talk about the four ways of generating the out of plane rotations. So this is one extended object. There are two beams which are trapping it. One is here, one is here. So in this case, one of the beams has been pushed in. The focus has been pushed in. So by doing that, what happened here, it was completely flat like this, and then we have generated an out of plane rotation. This is the first way of generating that. Let's see if this thing works. Yeah, this thing is sort of working. You'll see that the color is changing after a while. It will sort of here it will sort of, the color will become reddish, and then it will sort of, one beam will be turned off. Yeah, here. And then one beam will be turned off suddenly, and it will go back to the original configuration. You are not seeing it very well here because this is under bright field microscopy, but in the pitch detection system, you will see clearly that it sort of turned in the out of plane sense, because it has to be done under cross polarizers, remember. So then that was the first way of generating it. The second way of generating, in all of these cases, you need two stimuli. One will be one optical tweezers beam and something else, either a second optical tweezers beam or a stage that has been moved. In this case, it has been pressed. We took the particle and put it onto a stage, and then we moved the stage transversely. So that sort of gave it the second stimuli. Now here in this case, the surface is kind of hydrophilic. So therefore, it kind of adheres to the surface because of forces like the familiar forces that happen in water, the colloid on the surface. And because of that, the particle actually turns here. You can see a dot appearing in the middle. So it's basically, if you take it in the cross polarizers, you will see that it is turning actually in the pitch sense. So that here, for example, in this case, you will see that as the particle is held constant at one spot, the thing has turned here. This is going up and this is going down, because it's kind of back and forth motion that we are talking about. So this is the second way of generating the pitch rotation. This is a rolling without slipping at a nanoscale, because the surface area is of the order of 50 to 100 microns, nanometers, And it is notoriously hard to get a rolling without slipping event and detecting it at the nanoscale, because if you have an AFM cantilever, what would you do is, I know the experiments, you take an AFM cantilever and put it next to a particle, and you will push against the surface, and for that you require particles which are micrometer size, or tens of micrometers size. Here this particle itself is 1 micron in size, and here you are actually finding out the exact angles here. So that this gives a rolling without slipping. Now if you want to change the surface, if you want to make it from hydrophilic, you make it hydrophobic or something, then you get complete slipping and then there is no rotation at all. So we have shown that in this paper, the RSC Advances paper, that we can get from the different configurations one surface to the other. There is also one more case where we have actually chosen diamonds, micro diamonds, which have a birefringence also. So that we have shown rolling with slipping. So the 3 cases we have covered in this sort of thing. And this has the added advantage that if you sort of, this has been pressed down, and so it is relying on the adhesivity of the surface. So you can find out the adhesivity of the surface in a different soft probing scale. So if you want to find the adhesivity of surfaces, you have to take an IFM cantilever and you have to poke it into the surface, and then that would actually fuse the tip into the surface, and when you pull it back, you get a configuration which is very different from what we have here, because this is soft probing, that is hard probing. The adhesivity comes around 1 millijoule per centimeter squared, and that will be about 50, I think, 50 something like that. So this is a completely different way of probing, and it gives you sort of individual bond scale sensitivities. So the third one is kind of, this was sort of suggested by Professor Ruben Ramos Garcia from Mexico, that if you optically trap a particle in a kind of a bulk, you also generate convection currents right in the middle of the thing. Now we sort of we were fiddling around, and we put a gold surface on top of this bottom surface, and we put a laser beam through it. We were surprised to find that actually this generates these convection currents right here, right at the surface itself. It is forming these convection currents. And then this particle, which happened to be hexagonal, it was sort of spinning nicely. It was sort of going round and round and round. So this is kind of a convection current that we have built up here, and this is clearly a pitch rotation. So this is the third way of generating this thing. We published it in Biomedical Optics Express, and you can see we put some polystyrene particles. You can clearly see this this thing going round and round and round. This is the convection current that we have generated with this gold particle, and this is a dictyostelium cell, so you can actually sort of rotate this dictyostelium cell and do tomography on it. And then if you want, you can also sort of do a surgery, microsurgery. You can put a laser beam on it, and you can puncture the cell, and you can put stuff in, and you can or take stuff out from there. So that there is also one more thing I would like to point out. Professor Yubing Sheng from Texas Austin, he has used this thing, and he has sort of taken a surface and made some coated it with some proteins and stuff, and he has found the sort of found that this rotation can be used to find like shear forces. If you this is generating shear forces, you can find the bond strength of these bonds that are forming at this thing. So they have cited us also. This was published in eLight, I believe. So they have used cells to actually turn it and then find out what are the bond strengths in the shear force case. It sort of partially sometimes breaks, sometimes it adheres. So when it adheres, it sticks, and then there is no rotation, but when it sort of breaks, it sort of slips freely. So that's the kind of logic here. So this is the third way, and the fourth way, we have this upconverting particles, the hexagonal shaped upconverting particles. We were fiddling around with these materials a little bit. We put in iron here. The sodium yttrium fluoride, we have put some iron and some doping of ytterbium and erbium, and we find that this material actually becomes ferromagnetic. So then you have a material which can be optically trapped because the heating is low. The problem with using sort of hematite or anything is that these materials absorb a lot of light. This is very high absorption coefficient, so it absorbs a lot of light, and then it kicks out of the trap. It just doesn't stay there. So here this refractive index is very conducive, and yet this has a very good magnetic moment comparable to the magnetic trap, magnetic tweezers things, beads that they use. This is comparable to that actually. So, and so you can actually, this is clearly you can do anything with that. You can actually generate yaw, you can generate pitch rotation, because it's just a turning of the magnetic field. You can turn it in whichever sense and it will give you that rotation. And we have detected this rotation here pretty well. You can see this is sort of going like this. Here the fringes are going by. That way you can tell it is a kind of a rotating also. So that's because it's a hexagonal shape, there will be some fringes going by. So we published it in ACS Applied Optical Materials recently, a few months back. And then I'll go into the applications. How much time do I have? So I'm going to the applications. This is where is it pitch rotation useful? Where is the pitch rotation useful? It is useful. Where does the dynamics break from pitch to yaw? It happens in proximity to surfaces. Think about it. If a particle turns like this and the surface is here, then you will have a slightly different dynamics altogether than if you have something like going around like this and your surface is here. So that is where the sort of the dynamics breaks. So one of the first applications we thought about was you take a cell, a biological cell, and then we land this particle on top of this thing, and these cells automatically have some fluctuations because of thermal fluctuations and some active behavior. This the membrane will be fluctuating all the time. So you can land it on that and then look at the fluctuations. Now one of the first things that we hypothesized was that this fluctuations, if one thing pokes out and the other thing doesn't poke out, you have a kind of a slope there. You have a membrane slope there. So that slope you can study. This slope is directly connected to the rotation of the particle, and that's the thing. So if it is slope is tan theta, the particle will also be approximately like that theta angle in small angle approximation. It will be rotating by theta. So that's the thing. So here, for example, we have got RBCs. RBCs, you can see this is fluctuating a lot. This has been done by phase contrast microscopy, digital phase microscopy actually. And you can see this is fluctuating. These are different configurations in the cell, I think with different amounts of ATP or all that. So using that, and just to highlight the point, this is the work from Vidisha Sinha's lab, which is already published. I borrowed one slide from here, just to show that this is how membrane fluctuations look like under IRM, interference reflection microscopy. And this is flickering here, there's nothing here. So this flicker is the membrane fluctuations that I'm talking about. So, and we did that. We sort of compared the vertical fluctuations, the normal fluctuations with the slope fluctuations, and we find that this is the power spectral density of the fluctuations. In this case, it happens to be 5/3. So this is slightly different configuration from what generally people see in a kind of a healthy cell. If you take the fluctuations there, you're going to see -4/3 behavior. The power law is going to go as -4/3. And the coefficient would be very complicated. It's kind of 2-3 parameters in there. The bending rigidity, the cytoplasmic viscosity, and sometimes even the tension, that is the membrane tension. So finding it out accurately is a problem. So, but then when we did the slope fluctuations, we saw this kind of a behavior. So here the slope goes as -1, the exponent to the power law goes as -1, and there is a coefficient associated with that. So we sort of thought about modeling it and calculating it theoretically. So we assumed that the slope is going as tan theta is equal to y2 minus y1 divided by x2 minus x1. x2 minus x1 is kind of the base area of this particle that we have landed on this thing. And the y2 minus y1 are the different the heights of the membrane fluctuations. And then this, in the small angle approximation, theta is approximately, because it is optically trapped and it is not going to change too much, you know. So then it's a small angle approximation, so it's delta y over delta x. Then it becomes a gradient of heights, and that is the key thing. And then you can map it exactly 1-to-1 with the height fluctuations, height correlator function that you have for calculating this membrane fluctuations. So you can then take the this theta correlator is going to be just this gradient correlations. We did that. And we find that there is a kind of a Q sitting here, which is the additional term in the power spectral density integral. And if you calculate that, you're going to see that this power spectral density becomes kT over 6 alpha omega. Omega, as you can see, it's omega to the power -1. That's we get about 1.2, in the slope fluctuations. And this alpha, you can see there's just one parameter, that's the bending rigidity here. So you can find it very accurately. We published this in Soft Matter, and thanks to Manoj, I believe he's not here today. But so he did the calculations for this, this thing. And then we sort of moved ahead, and then we sort of tried to sort of use it. So one of the first applications that came to my mind was to, because there's some sort of, because of actin activity, there's some sort of, there's a kind of a cytoskeletal network underneath the membrane. It's called a cortex. This cortex, if you depolymerize the cortex, what happens? That was the question we had asked. So we find that this power law of the slope fluctuations is -1 again, nicely -1. And I'll come to this part a little later. And then you can see the amplitude is somewhat like this. But when you sort of put the lateranculin B, which sort of depolymerizes the actin, the amplitude went up. It's off by a factor of 5, the change in amplitude. Now this is quite consistent with the previous coefficient, because the bending rigidity is 1 over kappa actually. The coefficient is 1 over kappa. Kappa is the bending rigidity, or in this case alpha. The bending rigidity changed by a factor of 5, so it went up by a factor of 5. So you can read it off from here that how much the bending rigidity changed by. And this exponent remains -1 or 1.2 about, thereabouts. So you can sort of explain that slight difference by accounting for the fact that the particles are finite size. This is not point particles. These are sort of 1 micron birefringent particles. This is RM257 again. And so we also, in this case, because it was kind of an active, this actin cytoskeletal network, there is kind of an active poking going on. So we thought we should since we are depolymerizing the actin, let's look for active features, how the active features change. So we find that we have a theory for that. We sort of talked to Professor Neil Gau from Weizmann, and he already had a paper, and we sort of changed a little bit to introduce the slope fluctuations. And this is kind of a model that tries to fit it, but we could not see any sort of a change in this low frequency regime till like 0.2 hertz for this actin dynamics. So what we hypothesize is that this actin dynamics is happening slower than 0.2 hertz. We believe it happens at the order of minutes. And then this, we believe that if you sort of study it slightly lower frequency, you should be able to see these actin fluctuations also. So this is kind of the active fluctuations. This is the passive behavior, and we recently published this in Physical Biology. It published sort of accepted 3 days back. So that was the thing. And then the second part is this one. The second application is this one. So this pitch rotation, where else is it of use? Where else is it of use? This is in collaboration with Dilip. So you have this p-nipam interface, p-nipam particles, and then you sort of take this birefringent particle and put it on the interface, trap it basically on top of the interface, and then sort of study the dynamics. So as this has been hypothesized from the 1990s onwards, that you will see different modes of rheology actually. These are not the same modes of rheology. This is not like in bulk where all directions are same and everything is same. So here along the interface you will see different behavior. Orthogonal to the interface you will see different behavior. So in this first 2 modes, this is transverse mode and the horizontal shear mode. This gives you the pitch rotation actually. This is the pitch rotation, but nobody knew how to determine it. How to find it out, nobody knew. So, and then the compression mode is X. Shear mode is yaw, and this vertical compression mode is Y, or in this case Z actually. So talking about the compression mode, you can see that this is a kind of interface which has p-nipam on it. So initially the surface doesn't have too much p-nipam, so it's kind of viscous. Everything is kind of viscous, and then as the p-nipam forms, the interface forms a kind of a monolayer forms. It becomes jammed in there, so it becomes viscoelastic. Merenjo's Dilip student had done an extensive work on this thing earlier. So we simply built on that. So we see this is kind of a viscous, it's kind of a Lorentzian nicely, and then it goes into a viscoelastic form. We use a model with the frequency dependent viscosity. And then this clearly goes from here to here. This mu p is the kind of the polymer viscosity, which is the extent of viscoelasticity in there. This indicates elasticity. And this Z also shows that a sort of viscoelasticity happening. The coefficients are slightly different. This is less viscous than the x-axis, which is what you expect, because x is going to be most affected by jamming. And then the third mode is the pitch rotation. Here also, which is non-trivial actually. So how does this thing happen if you sort of jam it in? So here, as it initially is free, it is sort of quite Lorentzian and it's viscous. But then as you sort of go along and as the network of pinipalm forms, it becomes viscoelastic. Even in the your sense, even in this mode also, it becomes viscoelastic. So all the three modes show that. So this is the first time it has been studied. So it can have potential a lot of applications actually particularly in the interfacial rheology. Yes, please. Yeah, this actually see, the thing is this we can average it over. We can average it over like multiple shots, 10 shots or something, and then the fluctuations would be lesser. But there's no exponent. This is a Lorentzian actually. This is not x square. It's 1 over omega square plus x square. Mm-hmm. So yeah, so the thing is, the reason I'll tell you what happened here, this thing dries out very fast. So the interface just kind of rapidly changes position. So if you wait for 10 shots, by then the interface is already gone from this location to somewhere under that, because we have this under 100x, so we are actually seeing it at a very like precise level. So any small changes to the height can get easily sort of detected. So we did one shot only here. We could average this thing down and make it smoother. Of course, we can make it smoother by simply averaging it properly. Yeah, Lorentzian is from, this is how optical tweezers, if you put it in bulk or something, this is generally a Lorentzian. Because you can think about it in this way, gamma x dot plus kx equal to some Gaussian dependent random noise. And if you sort of solve for that, you get a Lorentzian actually. So that's the thing. And so in this case, this is simply we made it from viscous, this gamma, we made it viscoelastic. So using a generalized Maxwell's model, or in this case, Jeffrey's model, which sort of derived from some first principles using his advisor, Rono Joy. So he helped us with that. So that's the thing. So in all the three modes have been found out. Now I go to the third application in the intracellular rheology inside the cell. So you can see here this particle this is actually a dictyostelium cell, an amoeba cell which has been moving, and this particle is held at the same spot, you can see, because it has been optically trapped. So it is optically trapped and it is at the same location while this is executing all this beautiful dynamics. It's just going in an amoeboid fashion. Let me see if this video plays. You will see that this is also doing something similar here, this going back and forth and all that. This is free actually, but this one is not doing anything because it has been optically trapped. So this is a cell, MCF7 cell, polystyrene particles trapped in an MCF7 cell, and this was moving back and forth while this is held constant by the tweezers. So using this, you can also figure out the rheology inside the cell. How do you do that? Let's talk about it. So in the inside, the interior of the cell kind of has the cytoplasm is comprised of a cytosol, the fluid that into which it is sitting, which has proteins dissolved in it, and a sort of a network of fibers. It's called the cytoskeleton. So actin, myosin, microtubules, and then intermediate filaments, these kind of comprise this internal network. And inside this network, it is sort of moving back and forth. And of course, there are motors and all that, so it is sort of constantly doing a lot of things. There's kind of activity, and there is kind of a passive dynamics due to the material properties of the system. So this is, so we thought about comparing the translation and the pitch rotation inside the cell. Now, we ran into a problem. The problem was as follows. You see, if you put a tracer particle of 5 nanometers, you'll see a different rheology, or if you see a different viscosity than if you put a tracer particle of 10 nanometers. As you increase the size of the particle, the viscosity will change. You'll get different results. It kind of goes up to a point about like 100 nanometers where it kind of becomes constant. So different probe sizes will have different results, and there's kind of somebody who wrote an ACS nano paper out of it also. So it also depends upon how fast you're pulling, because if you're pulling slow, it kind of depends upon the ratio of velocity divided by the radius. The V over A ratio thing depends, it kind of gives you a viscosity value which is very different for different velocities and all that. The speed of pulling also matters. So in this complicated situation, how do you deal with it? So we chose a particle which is about 1 micron, which is in the flat region of that curve, and then we used passive detection for that. So we used a model which is, as I was telling you, the Jeffreys model or the generalized Maxwell's model. We derived it from first principles from Stokes-Fowler-B model, and we found the power spectral density here. This was published in Journal of Physics Communications in 2019. And then this is what we sort of get. This is something we are still building with Rajesh. So this is the kind of PSD for a translational motion, and at high frequencies beyond about 10 hertz or something, this fits very nicely to a passive thermal kind of PSD. And at low frequency, you will see this active behavior. This active behavior inside the cell is also visible, and it has been corroborated many times by Timo Betts and company all over the world. They are getting it. Even Daisuke Mizuno is doing these things, and he's showing that at low frequencies he's seeing this active behavior in this sort of just the fluctuations of the particle. They generally what they do to find out what is the sort of non-active curve is that they sort of take this particle and then they move it deliberately at a certain frequency, and then they study the dynamics at that frequency of the system of the optical tweezers. They move the tweezers and they see how the particle was moving, and by that they'll get some curve that does not depend upon the activity of the cell actually. So that is kind of the background. So but since we figured out this thing with Rajesh, he did this work. He collaborated with us theoretically. So he showed that if you make the V equal to 0, we sort of fit into an active model where the minimum of the model is moving suddenly here and there randomly around the place at a certain time scale, and that is also the standard model that people use in optical in the community. Timo Betts has also been using that. So we adapted that model here, and we made the velocity equal to 0, and then we get the passive trend here. Which does not have the active behavior, and we are still studying this thing. This is a work in progress. I just wanted to highlight this thing. So you can see both the active behavior and the passive behavior, thermal behavior. And then we compared the pitch and the XPSD, and we sort of have this is kind of thermal PSDs are pretty well, and this is the active region. And we compared this at low viscosities, it is sort of matching pretty well 1:1 with this thing, but high viscosity is kind of much more complicated because it sort of gets tangled in the network, this cytoskeletal network, and also the cells can start to die and all that. So it kind of depends on pockets of what you're considering. It has to be done a little more carefully. The X viscosity ratio matches pretty well, but the X relaxation time is all over the place again. So this still needs to be studied. This was published in Frontiers in Physics again, I think in January. So, and then to give you a sort of where we stand in mechanobiology using optical tweezers, you have got the physical properties, the disease diagnosis. Basically, you have solid stress, you have viscoelasticity inside the cell, you have on the membrane. That these two I have showed in this particular talk. And then you have got solid stress at the epithelial cells, for example. You'll see the extracellular matrix behaving certain way, and then you can study it for fundamental mechanobiology. You apply a stress, and you sort of see how the system responds. The system is actually called a poroelastic network because there is kind of the filaments and the fluid, and you can also use it for therapeutic mechanical stimuli, as in you see that that disease has happened, and then you give it a sort of a stimulus, and then you can cure the disease. This is kind of futuristic kind of thing, where in future you will be curing diseases in this fashion. You will apply a stimulus, maybe a pressure applied on the system, a hydraulic pressure or something, and then the diseased cells would be cured or something. This is kind of futuristic. We think about it this way. So that's kind of what we want to do, and so that's the thing. And I'll briefly talk about how much time do I have? Okay. 1 minute only. Okay, I'll finish. Okay, so this is kind of hydrothermoplasmonic trap. I told you about this pitch rotation in this sense. So here we have the same thing. I have two spots here, one laser beam here, one laser beam here, and then you will see that the particle actually got confined here, and you are moving, it can controllably be moved from one side and then it will be back to the other side also, just by changing the intensities of the lasers. You will see that there is a particle here and then a collection of other particles here. So this is kind of one of the lowest trap stiffnesses that you can get. It's femtonewton traps. You can sub-femtonewton displacements you can get. So this is kind of Rajesh's calculation again. So he has shown that this is kind of because of thermophoretic behavior, and the rest of it is microfluidics, like the fluid behavior. So just briefly that, and then I go into hot Brownian motion. So I sort of showed that if you have this upconverting particle and you excite it to 975, it gets trapped. But then when you emit this also, when you sort of absorb 975 radiation and it emits an visible radiation, then the efficiency is like 2%. So much of it is just lost as heat. So in the bottom side, you will have a higher temperature than the top side, and then it sort of acts like an active particle trapped in optical tweezers. Then you sort of get a kick. So we use that, and we calculated the MSD. We see an active behavior here, and this does not happen at a frequency which is not 975. 1064 nanometers will not give it this kind of a behavior. It gives a straight line instead. This kind of diffusive, and so you can see we can get from the active to the diffusive just by changing the wavelength. So using that, we sort of generated a Stirling engine. The idea behind that was the activity can be controlled by the intensity of your 975 laser, but the 975 also changes the trap stiffness. So how do you control that? You use a combination of two lasers. You keep the intensity constant and you ramp down one and increase the other constantly. So that's what we did. We sort of in the isothermal compression part, the trap stiffness, the 975 intensity is constant, while the 1064 intensity is gradually going up. In the isothermal, you are supposed to make it more stiff, the trap stiffness, and that's what we do. And then here in this isochoric heating, you sort of reduce the trap stiffness of 1064 while increasing the trap stiffness of 975, so that you get a higher activity while keeping the trap stiffness constant. And then you have the isothermal expansion part, where you keep the 975 intensity constant, 1064 goes down, and then vice versa for the isochoric cooling. So this is the kind of the velocities you get, and the trap stiffness. The trap stiffness you can see is going up, but the velocity is constant. Here the velocity is going up, but the trap stiffness is constant, and so on and so forth. So we generated this KV diagram, the kappa trap stiffness with the velocity, the active velocity diagram, and you can clearly see a sort of a loop here. So that sort of gives you the active, the Stirling engines kind of the loop, the behavior there. So yeah, so just to finish, the out of plane rotations was found important enough that the international community asked us to write about in the roadmap for optical tweezers. We wrote about generation and measurement of torques, and this particular thing in section number 15. Actually, it's 14. Slight change. So, and then this is the group. There was a postdoc, 2 students graduated, and actually the third one has also submitted thesis, and this is there somewhere here. So, yeah, thank you everybody. So this is the lab. This is sort of the space that I have, and I thank also welcome DBT India Alliance for the intermediate fellowship. So yeah, thank you. I'll take questions if you have.
Do they have any significance?
Which one?
Go back. Your power laws and stuff like that. Yeah, this one for example, the one you just
Yeah. So what happens here is that it's sort of now in the optical tweezers domain, because optical tweezers will act and make it flat. At the end of the day, this part is actually just flat, because the optical tweezers basically obstruct the motion. It confined it to a certain thing. So the motion there. So what will happen is it just becomes flat here. So this is the beginning of that actually.
Which physical scale is it tied to?
Which physical?
Is there a physical scale it is tied
yes,
to?
Yes, it does. Depends upon your trap stiffness of your optical tweezers thing. It's 0.01 seconds here, which would correspond roughly to about 100 hertz, slightly less than 100 hertz actually. You can account for 2 pi.
I noticed another kink in a slightly earlier graph. Before that. Before that. Here. The initial part.
This one.
Yeah.
This is the active region. That's what I'm telling you about. So it is actually probing both the passive thermal part and the active part inside the cell. Because there are molecular motors. This is exactly a topic of intense research. This thing is just about to begin now. Some people are already publishing big papers, Nature Physics and all these things about these active fluctuations. I know that you can either do it inside the cell or you can do it on the membrane. And you will RBC Timobets published in Nature Physics also. So it's just beginning to happen actually. People are starting to take notice of this thing. This particular measurement will give you this kind of a feature which is active, while the rest of it is just passive thermal. Now it depends upon, people say that where does the passive region start? Now that's a question of debate right now. So where till what frequency is the passive active region extending? It can be 100 hertz, it can be 10 hertz. Here we see till 10 hertz. If you change the feet a little bit, it will not change too much the curve. So we are finding that in this region this is active. As in, this is not thermally induced. These are the molecular motors or something that's carrying the cargo and all that. So it is sort of, this is kind of, the behavior is super diffusive, and it is kind of active in ATP dependent activity, you can say.
Okay.
That's what it is.
Thank you.
Yeah, Basu, it's a nice talk.
Okay.
This is regarding this magnetic rotation that you are talking about.
Yes, sir.
So, is it an AC field that you apply?
This is just a bar magnet you take.
Yeah.
You take a bar magnet and
Yes.
you just wiggle it around. If you turn it like that, the magnetic field will turn.
You are
So-
changing the position of the magnet. So that
we did make it more controlled. We have now, just like a magnetic tweezers these days happens, we have a needle kind of a probe, needle probe with windings on top of it,
Okay.
and that generates a kind of a strong field because it's now a point tip. So it will generate higher field. So we could with that generate about 200 Gauss. So we can actually do it alternating field. When we actually, that's a good point, because we see that if you make it alternating fields about 50 hertz or something,
Correct.
it also heats up the sample.
exactly, yes.
It's kind of it also heats up the sample. So
Okay.
we can use it for hyperthermia actually.
Applications also. you can
Yeah,
just
this
think
kind
of
of
it, yes.
cancer therapy and all that we can do.
Okay, so, and also you said it's a ferromagnet.
It's a ferromagnetic.
What kind of material is it?
So it's the basic structure is sodium yttrium fluoride with ytterbium and erbium doped with iron doping in it.
Okay.
And what happened as a consequence, our Ranjit Nanda did the calculations, the DFT calculations for us, and then this ended up becoming ferromagnetic because of the iron doping in it.
Okay. So the second, my question is that regarding that Stirling engine you are talking about, right? You are just the mechanical engine. How does it compare it with the efficiency or anything?
So we did not compute the efficiency, but I'll tell you this KV diagram that I talked about, the draft stiffness velocity. I should say Professor Rajesh Ganpati from JNCSR has been trying a lot to generate this KV diagram with his passive particles. He hasn't been successful in generating. We could do it because our particle was active. So that was the thing. He has an alternative configuration where the particle is passive and the bath is active. And it's less efficient because you can think about it. You have to generate the heat over the entire region. And while we have to generate heat over a smaller region, so it's more efficient.
Okay. Thank you. Thank you.
So I have this general question about if you put a tracer inside a cell, in the cytoplasm, what kind of diffusive behavior does it exhibit? Some people say that it could be super diffusive because of activity.
It depends upon the time scales, sir. It depends upon the time scales. As I was telling you here, this is kind of low frequency, around 10 to 100 hertz, somewhere till that point it is super diffusive. It is actually active because of the cargo being carried. After that, it becomes passive thermal. So it is kind of thermally induced kind of fluctuations. So it depends upon the time scales actually.
But I have also read some things about, since there are lots of obstacles inside the cell, the diffusion actually becomes, I mean,
Confined. So
sub-diffusive. I mean, it's not.
So if you sort of take this is kind of this model is not just passive thermal, it's viscoelastic kind of a thing. So we are considering that as a kind of an elasticity behavior. So it's not just free viscous, it's kind of becoming viscoelastic. So that is the kind of underlying assumption that we have. It fits pretty well to this model. Now if you sort of drag this thing at a certain velocity, then you get all kinds of behavior, because as I told you, the speed of velocity, the speed with which you're pulling also makes a difference. Then it becomes a poroelastic medium. That's how people showed it. That was also in Nature Materials, actually.
I see. Okay, thank you.
Any more questions? Okay. Thank you.
Okay,
Thank you, Basudev.
thanks a lot.